Before I move on and explain why quantum computers are so special, structurally speaking, why do they even matter at this conjecture? You may say, some of you might be thinking, why am I even spending 2 hours of my time here listening to another guy talk about quantum computing? Well, the your answer to this question is this: quantum computers are extremely important at solving some of the major issues that have plagued humanity for for several decades now. The first being the fact that let's take a look at encryption. Now, almost any national state that's worth its money has a method of encryption known as RSA, where each of the letters stand for a separate a gentleman who invented the concept. Now, how the RSA encryption method works is, just think of a number, think of an extremely big number that can be expressed as the factor of two or more prime numbers. Now, while this might seem simple, that is exactly how nations encrypt national secrets. Because if you think about it, as long as your key is big enough, there is no way to encrypt it correctly. But quantum computers are where things get wacky. Quantum computers have the ability to break traditional encryption methods. They have the potential to do so. I'm not saying they have the ability right now, but they do have the potential to do so in the future, thus throwing a country's um, entire vault of secrets into the air. That's why governments, as of currently, are spending tons and tons of money into research on quantum computing. And quantum computers have also been theorized to be useful in cancer research and several other such issues. Now that I give you an idea of how why quantum computers are important, let's look at what how exactly they're structured. Now, obviously, all of you would be familiar with the classical bit, the basic logical unit of the classical computer. The classical bit is divided into two discrete states, on or off, 0 and 1. Quite intuitive. These are discrete states. They are separate from each other, and one is completely distinguishable from the other. The it's a object capable of assuming only two states, and as I stated before, every problem, regardless of its complexity, can be translated into just a combination of zeros and ones. However, However, the quantum equivalent of the classical bit is the qubit or the quantum bit. Now, qubits have the ability to hold on to multiple states at the same time. How, you may ask? That's what we will see throughout this workshop. But quantum computers, as of this moment, all you need to know is qubits are the logical equivalents of classical bits in quantum computers, and they use subatomic particles such as electrons and protons that generally act as qubits within a quantum computing system. And generally speaking, electrons are preferred over protons for this qubit selection, because of the structure of the atom, because electrons are just easier to pick off and use. All right. And how can you implement a qubit? That is a logical unit which can be which is possible, which can exist in multiple states at the same time. Now, some of the ways you can implement a qubit is via nuclear spin, where 0 represents spin up and 1 represents spin down. The existence of photons in a cavity, where no photon indicates 0 and the presence of a photon indicates 1. Atomic energy levels, where ground state indicates 0 and an excited state indicates 1. Some other methods include stuff like photon polarization, where where a horizontal polarization implies 0, whereas a vertical one implies 1. Superconducting or trapped ions are also used in order to display a qubit. But before we get into that, take a look at the equation present up top. Now, this equation is basically ket psi is equal to alpha ket 0 plus beta ket 1. Now, before we delve into any more concepts behind quantum computers, let me just initiate you on a bit of the math behind quantum computing. Let me just share a whiteboard. I hope my screen is visible. All right. So now, generally in the quantum realm, any physical quantity that matters, that is a vector. One second, just a second. I'm sorry. A vector is generally represented in the quantum realm as a variable, say psi, and this psi is generally present in two notations: a ket psi, or a bra psi. These notations are generally termed as direct notations. These notations are generally termed as Dirac notations, and they're extremely widespread within quantum logic. This kind of notation is called a ket, whereas this kind of notation is called bra. Now, if you're keen enough, you'll assume that you can see that these notations don't get their names randomly. They just add up to a bracket. That's effectively why it's just the name bracket, and then they're split into bra and ket. That's all. It's nothing much. Now, generally, vectors in quantum spaces are represented in the form of matrices. For example, ket psi is generally represented by a column vector as a matrix, like say A, B, C, D, and so is bra psi. Generally, all vectors are expressed via a matrix notation, and via matrix notation, and ket bra. These are ket and bra. And another thing, interesting thing about vectors in the quantum realm is that, say I have a vector ket psi, which is say A, B, C, which is the matrix say A, B, C, D. The vector ket psi can be expressed as alpha ket 0 plus beta ket 1. Now, what this means is that the vectors ket 0 and ket 1 superimpose in order to form the vector ket psi. Or in other words, the vector ket psi can exist in the states both ket 0 as well as ket 1, where ket 0 and ket 1 in the quantum realm are represented by the vectors ket 0 is equal to I'm sorry, ket 0 is equal to 1, if I'm not wrong, 0 is equal to 1, 0, and ket 1 is equal to 0, 1. Now, how you may ask, how are I've been talking about kets the entire time, but how are kets and bras interrelated? Now, basically, a bra vector is nothing. Say I have a ket vector ket psi. All right, assume. Then ket psi is nothing but bra psi star. The star indicates that bra psi is nothing but the transpose of ket psi with all its elements undergoing a complex conjugate. For example, say my ket psi is let it be the matrix let it be the matrix I comma minus I, then bra psi will just be minus I. All right. It's just as you can observe, it's just the transpose. Rows become columns and columns become rows, and each of the elements are replaced by their complex conjugates. Now that we understand the relationship between kets and the contemporary notation bra, we can look at a bunch of interesting stuff. Namely, we already looked at the principle of linear superposition, wherein say ket 0 and ket 1 belong to a vector space V, then the superposition of these two vectors also forms a valid vector which is part of the vector space. A general expression would be, say, ket psi can be expressed as alpha ket psi 1 plus beta ket psi 2. It's just the principle of linear superposition, and the physical meaning of it is the fact that the vector psi is a result of the superposition of psi 1 and psi 2, and hence is capable of existing in both of these states at the same time with the probabilities alpha square and beta square. Now, let's look at a couple of products that let's look at some of the operations that these vectors undergo that are useful. First is there's two main products that come into play. First being the inner product. I'm sorry for the handwriting, but inner product. So the inner product is nothing but, say I have a vector psi 1 and a vector psi 2. I want to find the inner product of psi 1 with psi 2. That's just represented as psi 1, psi 2. Or in other words, it's just the bracket of psi 1 with psi 2, or the bra of bra psi 1 multiplied with ket psi 2. Again, remember, psi 1 and psi 2 are your vectors. They can be represented in the form of matrices. Now, what's interesting is the fact that, say I have a vector psi, right? Again, alpha psi 1, alpha ket psi 1, ket psi is alpha ket psi 1 plus beta ket psi 2. All right, let's assume that I have a vector of this sort. Then the probability of finding the vector psi in either of these states, psi 1 and psi 2, I mentioned before, it's just alpha squared and beta squared. But how exactly do we get this? It's not arbitrary. Rather, the probability of finding the vector psi in the state psi 1, that is probability of psi 1, is nothing but the mod square of the inner product of the state with the vector itself. So this is nothing but alpha square. That's just me conveying the physical significance of the inner product. Another interesting fact about the inner product is the fact that it always, no matter, say I have ket psi 1 inner product with ket psi 2, it's always, without exception, returns a scalar. So it's the equivalent of dot product, one could say, with respect to the classical mechanisms. But what about the next product that I want to talk about is the outer product. Which is, funnily enough, like how the inner product was bracket of psi 1 and psi 2, the outer product of psi 1 comma psi 2 is nothing but the ket psi 1 multiplied with bra psi 2, which always gives a matrix. Now, an interesting thing about the quantum realm is the fact that it's not just the vectors, that is psi 1 and psi 2. These vectors are also referred to as functions or states. It's not just these that are expressed as matrices, but rather there's also something called operators, which, say I have an operator A, which acts on a state psi, or let's just keep it ket psi, and results in another state, say phi. this just means that the operator A acted on psi in order to get phi. But mathematically speaking, this when I say A acted on a state, what exactly do I mean by that? Well, it's nothing much actually. This operator A is just a matrix. It is just a matrix. A, B, C, D. It is not, it's just a matrix, it's nothing more. And A acting on psi is just a matrix multiplication of the matrix A with the matrix represented by the vector kit sign. Now, within quantum operators, which are extremely useful, there's two main things that we will worry about. Them being the There's two main things we need to worry about. Then being the Hermitian operator, as well as the unitary operator. First, looking at the Hermitian operator, which is represented, say, an operator H. This is nothing. A Hermitian operator is one where H is equal to H dagger. And what exactly do I mean by H dagger? H dagger is nothing but the transpose of the matrix and a complex conjugate of the elements of the transpose. Same as the star that I mentioned before. Same, it serves the same function. And a unitary operator is basically, say, if I have an operator U, then U into U dagger is equal to the identity matrix. These are just some common facts that you might want to keep in hand as we go through the workshop. Now that we know a little bit about the operators, how exactly do the what exactly do we call linear operators? Now, say again, let's just take the same example. Get psi is alpha get psi 1 plus beta get psi 2. Then a linear operator A, no, just ignore the alpha and beta as well for now. All right. So then a linear operator is one where A acting on psi is nothing but summation of A acting on psi 1 plus A acting on psi 2. That is then A is called a linear operator. And with respect to operators, you might have also come across I'm pretty sure you guys have heard about the Schrodinger equation, which is basically H psi is equal to E psi. Now this H psi is equal to E psi. Now this is nothing but H being a Hermitian operator. H is just the Hermitian operator. H is just a Hermitian operator. And psi is a wave function, which results in E, which is the scalar, which is a scalar that represents energy, E psi. This, if you look at this equation, then H is the operator, psi is the eigenfunction or the eigenvector, E is the eigenvalue. Whenever you have an operator that acts on a state and it just produces a scalar multiplication of said state, then the scalar that does the multiplication is called the eigenvalue of the eigenvector. All right. These are, and before we move on, let me just talk about what a basis is. Now, a basis, this is not anything you need to pay much attention to, but it would just be better if you guys knew about it. So a basis is nothing but the set of all vectors which are orthogonal to each other, normalized, and the superposition of any two vectors within the space results in another valid vector belonging to the same space. Now, what exactly do I mean by orthogonal and normalized? Now, two vectors, say psi1 and psi2, are considered to be orthogonal when the psi2 are considered to be orthogonal when the inner product of psi1 with psi2 is equal to inner product of psi2 with psi1 is 0. And they're considered to be normalized when inner product of psi1 with itself is equal to 1. The square of the inner product of psi1 with itself is equal to 1. Now, why exactly do we require this normalization? Normalization is basically this is nothing but say I have psi as alpha ket psi 1 plus beta ket psi 2. This just means alpha square plus beta square equals 1. This just indicates this. But why do we need this is the question. That's nothing but because of alpha square is the probability of finding the vector psi in the state ket psi 1, and beta square is the probability of finding the vector psi in the state psi 2. So this just means that the sum of the probabilities of all the vectors that form the superposition vector has to be equal to 1. It's just so that the sum of the probabilities is 1, nothing more than that. Okay, now that we have a very basic handle of the math, let's move on to the conceptual basis of quantum computing. Let me just share the slides again. Okay, I hope my screen is visible. All right. Now, as I said, the ket psi, the quantum state ket psi is alpha ket 0 plus beta ket 1. This just means that the vector psi, as I mentioned before, is capable of existing in both the states 0 as well as 1 with the same time, where alpha square and beta square denote the probabilities of it existing in that particular state upon measurement. The superposition principle, again, as I stated before, linear combinations of solutions to the Schrodinger equation of valid solutions. Ket psi is alpha ket 0 plus beta ket 1. The measurement probabilities, again, you guys want to look at it if my handwriting wasn't too clear, and a normalization factor. All right. Now, how does quantum superposition work theoretically speaking? And because unlike classical bits, which are just simple logical units, which can either be in two states at a time, either be in one of two states at a time, either they could be on or they could be off. But unlike them, qubits behave like waves. Rather, you can imagine a qubit as a wave function that can overlap without any interference. Then a qubit can also be represented as a vector on the Argand plane. The Argand plane is just the x plus iy plane, where x is the real part, y is the imaginary part. Whereas classical bits only lie on the real number line. A visual representation of it would be better. Yeah. So a qubit state can be represented on a 2D vector space, as can be seen here. Why I say 2D vector space is because when what we actually use for representing qubits as vectors is this geometrical structure called a block sphere. Now, block sphere will be explained in the later sections, but for your understanding sake, let's just assume the project a 2D projection of the block sphere. Let's take a vector ket psi, which is basically ket 0 plus ket 1. Now, this just means that since it's ket 0 plus ket 1, this means that the coefficients of both the faces of both ket 0 and ket 1 are the same, which means the vector is equally likely to be in either of those states upon measurement. Therefore, you can see that it's tilted equally towards both the 0 as well as the 1 axis at a 45-degree angle each. Now, if it were twice as likely to be in the one state as compared to zero state. For example, it where something like ket psi is equal to alpha ket 0 plus 2 alpha ket 1, then the vector would just tilt more towards the one axis, 30 degrees here, 60 degrees there. All right. And this is the single, this is one of the most important concepts that make qubits that much more special with respect to quantum computing, and that is this thing called entanglement. Entanglement is basically when two or more qubits become interlinked state by state. That is, the state of one qubit directly affects the state of another qubit. Now you could argue we could forge such a relation in classical bits as well. I take a classical bit, put it through a bunch of logic, get some complex circuits, and generate a solution that is dependent on another bit. Say I could do that, yes, but that is not that. But that doesn't mean that those two classical bits are intrinsically linked. That is, one directly affects the other. Whereas in quantum bits, that is exactly what that happens. Now let's take an example. Say I have two coins, right? And I toss both of them one after the other or at the same time, doesn't matter. I just toss the two coins. Normally speaking, the probability of getting two heads simultaneously is one fourth. However, if I considered, that is only if these I consider these coins to be classical bits. Now, if these coins were quantum bits and they were entangled with each other, such that the state of one directly affects the state of the other. Say the head states were entangled, then the probability of finding two heads is half, because the moment one coin lands in head, the other coin has to be head. This is basically quantum entanglement, and it's very useful, especially in quantum communication channels and so on. Very key to quantum computing. The ways you can generate a quantum entanglement artificially is either optically using parametric down conversion, laser or microwave control, and using quantum gates. To be more specific, the C not yet. But then we will be focusing more on the quantum gates concept in this workshop. Now Lippy will take over.
Okay, thank you, Shreyas. Okay, I'm gonna present the PPT. Just a minute. Okay. Okay, as of now, Shreyas explained about what is quantum computing and quantum bits. Now, as he mentioned, like how quantum bit can be expressed in an arcane plane using 2D, like in the coordinates of x and y, and using the angles. Now, block sphere. What is block sphere? It's just nothing but a geometrical representation of a qubit in a complex vector space using the coordinates. As you can see, this we're using a 3D sphere for expressing the qubit in a complex vector space. So what is this theta? First of all, let us consider a state psi, which is randomly existing in a vector space. Let's consider a state psi, and this state psi can be of any form. Now this angle can be, which is theta, is the angle between z-axis and state psi. And this angle 5 is the angle between x-axis and the state ket psi. So what does this tell? The block sphere just tells that where does this random ket psi we've taken exist in the complex vector space. Now, what is this ket 0 and ket 1? Shreyas already talked about what is ket 0. It is 1 comma 0 and ket 1 is defined as 0 comma 1. So 1 comma 0 and 0 comma 1 is nothing but where it exists. 1 comma 0 is the point, is a quantum state. So every point on this block sphere is considered as a quantum state where it exists in that vector space. So this block sphere helps us to represent where that specific vector space exists. So we have here spherical coordinates, but as you guys know, it is the calculations of spherical coordinates is very hard, very complex when we take for the calculations. So we're just gonna ignore this angle phi and just gonna continue with angle theta, so which is basically a circle with x, y, z coordinates. So this ket 0 and ket 1, I'll explain how do we get the values, how do we suggest the values of 1 comma 0 and 0 comma 1, how are we getting those values. As you can see, the coordinates here, the coordinates are cos theta by 2 and e power I phi sine theta by 2. The coordinates tells us where depends on the theta angle, what how much the vector makes an angle theta with the given z axis. That tells us the place where that particular state exists. So now we're gonna see how this ket 0 and ket 1 vector space can be expressed or suggested in a space. Okay, so this here ket 0, right? So let's take a block sphere. Let's consider a block sphere, and this is z-axis, right? Okay. Now this is, let's consider a random state psi in the vector space, and we know that this is theta. And if you consider this as x, this is angle phi, right? But we are ignoring this phi and considering the only theta. Now, how are we defining the state ket 0 in this block sphere? Let me show you that, right? Okay, so we're gonna ignore state the angle phi, right? So now we'll take a block sphere and this psi be ket 0. So the angle, the ket 0, the block sphere will be z axis, and as it has no angle, it will be on the same line or plane as z axis, which is ket 0. So here the angle between the z and the random state we've taken, which is named as ket 0, is the angle is theta is equal to 0, right? Yeah. So now we know the formula. This is a general formula of how a coordinate exists in a block sphere. So now we know the angle between the z-axis, and we've taken a random vector space and named it as ket 0, and we've assumed the angle between them is 0. Right? Now we're going to substitute the 0 degrees in the theta place. Now we'll get cos 0 and sine 0. We know the values as trigonometric functions. Cos 0 is 1 and sine 0 is 0. Now we got enough. That's why ket 0 is placed in the north of the block sphere, where we consider the angle between z-axis and ket 0 as 0 degrees. That's why it is placed at the north of the block sphere. And as you guys know, now 0. Now let's go to ket 1. How does this ket 1 arrived? Right? Okay. Now we take a block sphere, z-axis. Now we'll assume a random state vector being here, which we name it as ket 1. Right? Now the angle, see the angle. The theta is 180 degrees, which is pi, right? Which is in radians, pi. So now we're gonna get we're gonna substitute. Now this is theta. So we're gonna substitute this theta is equal to pi in the given general formula, which is cos theta by 2 comma sin theta by 2. And now we'll get cos pi by 2 and sin pi by 2, which we know the values by trigonometric functions, which is nothing but cos pi by 2 and sin pi by 2. Cos pi by 2 is 0 and sin pi by 2 is 1. So now we know why we get the block sphere, why we place ket 0 at the top, which is at the north, and ket 1 at the bottom, which is at the south. So now we've gotten a basic representation of a block sphere. So now we use this ket 0 and ket 1 as basics to represent any vector space. Okay, so now you guys learned about basis, right? What is a basis? He explained what's a basis is. Now what I'm gonna tell you how we're gonna use that. Ket 0 and ket 1 acts as a basis. Like, okay, let me tell you, if I take ket psi, I can define it in the form of ket 0 and ket 1. Let it be alpha ket 0 plus beta ket 1. I should be able to represent it in this form to this ket psi to exist in this vector space. That is basically basis. If this ket psi, what state we've taken, is existing in a vector space, it should be represented, it should be able to represent in the form of ket 0 and ket 1. That's what a basis is. So we use ket 0 and ket 1 as the basis. That's why we take ket 0 and ket 1 as the basis in the block sphere to use it to represent any form of state. So now you guys understood that. Now, yeah, as you can see, this is the superposition. Now I told about basis, right? Now you can easily understand. If we take a random ket psi, the superposition of a qubit is expressed as the linear combination of basic states ket 0 and ket 1. So basis, this that's why we call ket 0 and ket 1 as basis states. So if we take random ket 0, which belongs to that vector space, we should be able to represent it in the form of linear combination of ket 0 and ket 1. That's why we use this ket 0 and ket 1 as the basis states. And yeah, as you guys know about the probabilities, this alpha and beta, this alpha and beta are nothing but the probability amplitudes. Alpha square tells us about existence of ket psi in the state ket 0, and beta square tells about the existence of ket psi in the form of ket 1. Yeah, now you can see this in that. Ket psi is equal to alpha ket 0 as we take a random state. Now the probability of ket 0 will be alpha square, which means that this is the probability of ket psi being in the state ket 0. Probability of ket 1. The beta square means the probability of ket psi existing in the state ket 1. Normalization. Yeah, as Reyes explained about normalization, what is it? It's just magnitudes of both the probabilities should be equal to 1. Why should it should be 1? As we know that we use quantum mechanics to explain a certain complex conditions like Schrodinger equations. We use quantum bits and all these vector spaces, as we can't explain it by classical bits. So this normalization is used there to, because the scalars we take, it should be normalized. It should not be complex when we solve it. It should not be complex. It should be reduced, like, as simplified it is good to go. That's why we use normalization to simplify it. Now, okay, let's see an example. Now let's take a block sphere with angle pi by 2. That means the state is here. Let's take it as a kid psi, which is random state with angle, you guys know, pi by 2, which means 90 degrees, right? Now theta is equal to pi by 2. Now we know the basic formula of the block sphere, the coordinates of the block sphere, which is cos theta by 2 and sine theta by 2, right? So now we substitute that theta value in this basic formula to get this numerical. Okay, now we'll get the coordinates, which is 1 by root 2, right? We'll get both as 1 by root 2 and 1 by root 2. Yeah. So now what is this representation? We've known the coordinates. I told you guys, if we take random state such as psi in a Hilbert or complex vector space, we should be able to express in the linear combination of ket0 and ket1. That is this representation. These are like considered as alpha and beta. You can express it is in the form of linear combination of ket0 and ket1. That means this psi exists in this vector space. So now, if you take it as you know the values of ket0 and ket1, right? It's let me show you guys. Let's just basically 1 by root 2 comma 1 by root 2. This means this 1 by root 2 ket0 is 1 comma 0, right? And ket1 is 0 comma 1. Right? Which is basically 1 by root 2 and 1 by root, right? So this is basically this representation is just this. We're going to represent it that way so that it exists in the vector space. Now we know the probabilities. This let it be alpha. When we compare it to the general form, let it be alpha and let it be beta. The alpha square is 1 by 2, which is the probability, and beta square is also be equal to probability of ket1 and ket0 is the same, which is 1 by 2. So if we 1 by 2, if we convert into the percentage form, we'll get 50%, which the meaning is only 50%. The psi state existing in the ket0 form is only the probability is 50%, and the psi existing in this ket1 is 50%. This can be conveyed from these probabilities, right? Now you can see in one example. Now let's go to other example, which is theta is equal to 3 pi by 2. As you guys can see, it's just z-axis and 3 pi by 2, which is mean like till this, right? This is a random state psi, which has the angle 3 pi by 2, right? The spin, which means it's just theta is equal to 3 pi by When you substitute the theta in the general form, you'll get cos 3 pi by 4 and sine 3 pi by 4. Now, we know that by trigonometric functions, cos 3 pi by 4 will result in 1 by root 2 and sine 3 pi by 4 will result in minus 1 by root 2, right? Yeah. So now, if we expand, like explain it in the form of linear combinations of ket 0 and ket 1, we'll get this. As you can see from the previous slide, it's the probabilities are the same, but the sign is only different. It just basically means the phase is different. The phase is gonna change by 180 degrees, which you guys know pi by 2 and 3 pi by 2. Phase change will be 180 degrees. So that's how we're gonna see the value phi as 180, right? So this psi is will be equal to oh, sorry psi will be equal to this 1 by root 2 ket 0 minus 1 by root 2 ket 1, which is basically, as I introduced in the last slide, which is basically 1 by root 2 and minus 1 by root 2, right? So the probabilities are going to be the same, which is 50% each. 1 by 2 into 100, which is 50. That means ket psi existing in ket 0 is 50% and ket psi existing in ket 1 is 50%. So now let's go to two qubit system. Before going into the two qubit system, let me explain a product called tensor product. Sorry for my handwriting. Tensor product. What is this tensor product? If we take a ket 0 example and do a tensor product, okay, this is expressed like this. This symbol is used for tensor product. If you do like this, if we take two ket zeros and do the tensor product, you guys know the ket 0, which is 1 0, and which on tensor product 1 0, right? You guys, this is gonna be equal to 1 into 1 0 and 0 into 1 comma 0. This is basically tensor product. You will get 1 0 0 and 0. So this state, what is the state? This state is nothing but ket 0 0. Okay, this is basically a tensor product. Right, you guys understood, right? So I gave example for ket 0 and ket 1. You ket 0 cross ket 0. Now if you apply it to every ket 0 ket 1 and ket 1 ket 0 and ket 1 ket 1, you guys will get the forms 1 0 0 0 and 0 1 1 0 1 0 0 and 0 0 1 0 and 0 0 0 1. So this is basically ket 0 0 and like that. This is ket 0 1, ket 1 0 and ket 1 1. This is basically a tensor product, guys. You can apply to any type of matrices. This tensor product can be applied to any type of matrices, but we use tensor product in 2-qubit systems. Now, let's see what are 2-qubit systems. You guys understood how ket 00 is came from a single qubits. Now we'll see how it came. Okay, okay. Uh, Now, see, let's take a random state, psi 1, and another random state, psi 2. We're gonna do a tensor product. Now we'll get alpha 1, alpha 2, which is ket 00. Now I explained how it came, and which is generally 1000. And when you multiply it, we'll get alpha 1, beta 2, and beta 1, alpha 2, and beta 1, beta 2 as the probability amplitudes of respective ket 0, ket 01, ket 10, and ket 11. So the probabilities of ket 00 exist, ket psi 1 and psi 2 existing in ket 00 is alpha 1 square and alpha 2 square. This box is just to uh, easy to remember or understand how these probabilities are existing for these kets different 2-qubit systems, which is alpha 1 alpha square, alpha 1 square, alpha 2 square, alpha 1 square, beta 2 square. Now you right respectively. Now you guys understood what 2-qubit systems, right? I've showed you the general formula. This is basically the general formula of 2-qubit systems. How you can generate 2-qubit system from 1-qubit system, right? So now we'll take two examples, right? Which is ket psi 1 is when theta is equal to 60, we take it as ket psi 1 and we'll get root 3 by 2 ket 0. If you apply the formula, which is cos theta by 2 and sin theta by 2, we'll get root 3 by 2 and 1 by 2, which can be expressed as ket psi 1. And if you take another theta is equal to 120 degrees and substitute in the general formula, you'll get 1 by 2 and root 3 by 2. These are the probabilities, right? 3 by 4 into 100 and 1 by 4 into 100. So, respectively. Now, yeah. So this is the 2-qubit system of the before example I've taken psi 1 and psi 2 state, right? This is basically alpha 1 alpha 2, alpha 1 beta 2, beta 2, beta 1 alpha 2, beta 1 beta 2. So you can see the probabilities, which is multiplied by 100. You can see the probabilities, right? So this is basically the wave function of 2-qubit system generated from 1-qubit system. And yeah, this is probabilities. We've taken ket 00, ket 01, ket 11, ket 10, ket 11. So this is the probability as for the slide, this example I've shown. These are the probabilities. How each state, how the ket psi 1 psi 2 exist in each ket 00, ket 01. This is the probability of ket psi 1 psi 2 existing in this ket 00 respectively. Okay, now I'm gonna hand over it to Shreyas.
All right. I hope I'm visible. All right. Now, coming to single qubit operations, as of now, what we have learned is the basics behind the math of quantum computing. But now let's look at quantum computing itself. And the very basic of classical computing, as many of you would have come to understand, is just logical gates. There is the quantum equivalent of logical gates are your qubit operators. Now, quantum gates or qubit operators are basic operations that act on qubits, and they basically are the bedrock of all the concepts that are built in quantum computing. Any single algorithm that you write in quantum computing, you need a logical basis, and these operations provide that logical basis. Now, to be analogous about it, take the NOT gate in classical like in classical computing. What does the NOT gate do? It accepts a singular bit as an input and just flips it and displays that as the output. Now, single qubit operations are the same in the fact that they also accept a singular qubit as input. But it is what they do with that singular qubit that makes them so interesting. Now, as I said before, they're just basic operations that act on qubits, and a small set of universal gates is sufficient to perform any quantum computation, and these are some of them. First, the primary three being the X gate, the Y gate, and the Z gate. They're also known as the poly X, poly Y, and poly Z gates or operators. These gates effectively operate on these gates effectively operate on a qubit with respect to quantum computing, which means that mathematically speaking, the qubits act as wave functions that are acted on by an operator, that is the X operator, the Y operator, or the Z operator. These operators are called poly operators or poly matrices. They are represented by sigma X, sigma Y, and sigma Z respectively. What the X gate does is it basically acts as the quantum equivalent of the NOT gate. So when you pass a qubit through it, it basically flips the wave functions. It basically flips and swaps the zeros and 0 and 1 states. What the Y gate does is it rotate. If you now come back to the concept of the block sphere, what the Y gate does is when you take an input and pass an input qubit through the Y gate, it rotates the qubit by pi around the Y axis. And as for what the Z gate does, it basically flips the face of 1, whereas while keeping the phase of 0 as constant. Now, what do I mean by that? Take, say, just a second. That's fine. Okay, take a vector ket psi is equal to alpha ket psi 1 plus beta ket psi 2. Then alpha ket psi 1 plus beta ket psi 2. Now, when I pass ket psi through the Z gate, the output I'm gonna get is gonna be alpha ket 0, alpha ket 0 minus beta ket 1. That is the face of the 1 alone is flipped. When I come to that, you'll get to understand it more. Some other gates include the T gate, which multiplies the e to the power I pi by 4 factor into whatever is the face of the ket 1. By face of ket 1, I mean mathematically speaking, I mean the coefficient constant coefficient of ket 1 in the vector. For example, if I have ket psi is equal to alpha ket 0 plus beta ket 1, then beta is the face of ket 1 with alpha being the face of ket 0. And what the S gate does is it just rotates the qubit by pi by 2 around the Z axis. It's quite crucial in circuit synthesis. But the most crucial of all of these gates, generally speaking, is the Hadamard gate or the H gate. Now, what the Hadamard gate does is it creates a superposition from a singular qubit. Now, we'll come back to that later, but first let's explore the XYZ gates. All right. So first, let's consider the X or the poly X matrix or the X operator. So it's represented by the matrix 0, 1, 1, 0, as can be seen here. Say I have a vector ket q, which is represented by the column vector a, b. Then the operator x acts, which is 0, 1, 1, 0, acts on a, b. And as you can see, it just flips the bits ket 0 and ket 1. Or in other words, it basically swaps the amplitudes of a and b. The amplitude of a becomes b and the amplitude of b becomes a. 1 second. Just a second. Yeah, the amplitude of A becomes B and B becomes A. It's just the flipping of the amplitudes or flipping of the states. Now the X naught gate, again on basis states such as ket 0 and ket 1, when you operate it, it just results in a simple bit flip. 0 becomes 1, 1 becomes 0, as can be seen here. But its effect on superposition is what is interesting. Now let's take the superpositions. By superposition, I mean a vector that is made up of a superposition of two or more basis states. Let us consider the basis states ket 0 and ket 1 for simplicity's sake. Then the ket plus is basically 1 by root 2 times ket 0 plus ket 1, and ket minus is 1 by root 2 times ket 0 minus ket 1. Basically, plus and minus have the physical significance of being those vectors that represent the spin of an electron, because the spin of an electron could be either 1 or 0, right? Plus representing the upper spin and minus representing the lower spin. All right, now on superposition, the x acting on the plus remains unchanged, whereas x acting on the minus results in a phase flip. Mathematically, it's represented in the next slide, if I believe. Yeah, so x on the plus matrix, the plus matrix is nothing but 1 1. As you can see, mathematically, the x operator on the plus matrix results in it being unchanged, whereas on the minus side, the x operator on the minus matrix results in minus of ket minus. That is, the phase of the phase factor picks up the state picks up the phase factor minus 1. That is, the phase alone of 1 is flipped. Now you can see here that x on plus remains plus. This just means that the eigenvalue of this expression is 1, whereas the eigenvalue of this is minus 1. As I mentioned before, an eigenvalue is basically when eigenvalues basically come up when I have an operator that acts on a state and produces a scalar multiplication of said state. Here the eigenvalue is 1, and here the eigenvalue is minus 1. This just again, as can be seen, x on plus unchanged, x on minus produces a minus phase factor. And visually speaking, it's the x gate's effect on the qubit with respect to the block sphere can be seen here. Here while I say block sphere, here you can see it's a circle because we're gonna take a 2D projection of the block sphere. Now first take ket 0. You can see it's represented here. Passing ket 0 through an x gate, I get my bit flipped and I land in ket 1. And rightfully so, it's called the bit flip gate. And x gate on a superposition just swaps the amplitudes. For example, if I have ket psi which is equal to alpha ket 0 plus beta ket 1, my resultant would be beta ket 0 plus alpha ket 1. And if you can see that it's just that the amplitudes have been flipped, and it's just amplitudes just have been flipped. Yeah, and you can see here that this is a small summary of what the poly gates do. The x gate is a pi rotation about x-axis. Yeah, exactly. The bit flip results in a pi rotation about the x-axis. Here you can see that the qubit rotates by pi along x-axis. Here as well is just a natural consequence of flipping the amplitudes. Poly y results in a pi rotation about the y-axis, and poly z gate results in pi rotation about the z-axis, with the phase of 1 alone getting flipped, with 0 being unchanged. All right. Now coming to the most important of the gates is the Hadamard gate. Now the Hadamard gate, logically speaking, is the simplest of all gates, but it is nevertheless the most important, because in all the gates that we have seen as of now, and that be it the x gate, the y gate, or the z gate, you enter a single qubit into it without any superposition, a singular qubit, say ket 0 or ket 1. Your resultant is also of the form of a singular qubit, and when you enter a superposition through it, the resultant is a superposition. Say if I enter ket plus, the answer ket plus through the x gate, the answer was ket plus. And when I entered ket minus, which was also a superposition of zeros and ones, through the x gate, my answer was just minus of ket minus, which was still a superposition. However, the Hadamard gate is where these things differ. Now, the Hadamard gate is generally represented in the matrix form as 1 by root 2 times 1, 1, 1, minus 1. Actually, before I continue on with the Hadamard gate, And the 1 by root 2 here is just the normalization 1 by root 2 here is just normalization factor. Same is can be seen as the case here. um Let me just go. Yeah. So here ket plus and ket minus, it's 1 by root 2. If you may observe the scalar, both the quantities are multiplied by the scalar 1 by root 2. This is because so that the ket plus and the ket minus vectors are normalized. The 1 by root 2 is nothing but the normalization factor, so that the sum of the squares of the probabilities add up to 1. Yeah. Yeah. So H is represented in the matrix form by 1 by root 2 times 1, 1, 1 minus 1. But where it becomes interesting is if I pass the Hadamard gate through a zero vector, zero ket, it produces an equal superposition. It produces H through 0, produces the plus, whereas H through 1 produces the minus, which means when I pass a singular qubit through the Hadamard gate, the result is an equal superposition with phase. And the interesting thing about the Hadamard gate is that it is also self-inverse. When I pass a superposition through the Hadamard gate, the resultant will be the singular qubit with which produce the superposition, as can be seen here. Passing ket plus state through the Hadamard gate will result in ket 0, and passing the ket minus state through the Hadamard gate will result in ket 1. Basically returns it to its base state. Now the effect of Hadamard gate you can see on the states. Now H ket 0, H passing through ket 0 will result in 1 by root 2 times ket 0 plus 1 by root 2 times ket 1. Again, this is equal superposition because you can see that both ket 0 as well as ket 1 have an equal probability here, 1 by root 2 being the normalization factor. And H gate on a, let's see the effect of H gate on a random superposition. For example, say I have a vector ket psi represented as alpha ket 0 plus beta ket 1, as can be seen here. Passing this superposition psi through the Hadamard gate H will result in alpha plus beta by root 2 times ket 0 plus alpha minus beta by root 2 times ket 1. This is basically just the sum, ket 0 state, the phase of ket 0 being the sum of the amplitudes, and the phase of ket 1 being the difference of the amplitudes. Here again, do not get confused by the root 2. It's nothing but the scalar normalization factor. And as you can see, in a superposition, this is the effect it does. Visually, it's represented in the block circle using this. All right, just for a quick summary of what we discussed, the X gate is the bit flip gate or the quantum equivalent of the NOT gate. When you pass a singular qubit through it, it just results in a flipping of the bits. And when you pass a superposition through it, it still results in a flipping of the bits, but it could also be interpreted as the phases getting the phase of one being the phase of the other, and so on, and vice versa. The Z gate is just the phase flip of 1 alone, whereas 0 remains unchanged. It's also physically represented with respect to the block sphere as a pi rotation around the z-axis. Here you can see alpha ket 0 plus beta ket 1 through the Z gate becomes alpha ket 0 minus beta ket 1. Hadamard gate, it's just produces, it's a self-inverse gate, and it produces in superpositions when taking qubits as inputs, and since it's self-inverse, when you give the necessary superposition, you will return back to the base state. And on a random position, and if I pass a random superposition alpha ket 0 plus beta ket 1 through the Hadamard gate, it will result in alpha plus beta ket 0 plus alpha minus beta ket 1. Basically, the phases get added up, and that becomes a new phase for ket 0, and the difference of the phases will become the new phase of ket 1. Root 2 is the normalization factor. T gate, or the pi by 8 gate as it's otherwise known, is nothing. It's very simple. It just multiplies this factor e to the power I pi by 4 into the already existing phase of ket 1. For example, let us take the our common example, ket psi is equal to alpha ket 0 plus beta ket 1. Then our resultant will be alpha ket 0 plus e to the power I pi by 4 beta ket 1. All right. Now, moving on to 2 qubit operations, Lipi will take over now.
All right. Uh, Let me share my PPT. Yeah. You guys still now understood how single qubit operations are like, which is X, Y, Z, and Hadamard gate, which differs. Okay, XYZ gates are, as Shreyas said, when you take a single qubit as get zero, you'll just operate on a single qubit to get another single qubit which has phase difference or like NOT gate or representing any gate. And come to Hadamard gate, it's just when you take a single qubit, you apply Hadamard gate, you'll get a two qubit system. Now here in this two qubit operations, what we're gonna do is that we're gonna take two qubits directly. Like if you take 0 and 0, we're gonna operate two qubits from the start. So what is the C naught gate? It's the C naught controlled C naught gate is a two qubit quantum logic gate, which means it is applied on two qubit logic gate. If you consider, let's take a generalized A and B. These are the two qubits we are applying this gate on. Okay, and in this CNOT gate, what you're saying is that there are two different types of qubits where we differentiate, which is one is control and one is target. Right? What is control means? What is target means? What are these? Why are these terms we are using? Control is just that when the qubit is 0 in the control qubit generalized form, if the qubit is 0, the target qubit is not changing. If the qubit is 1, the target is qubit is going to change to the target qubit is going to change to 1, which acts as a NOT gate. If you take a control qubit as 0, the target qubit you observe it's not changing. It's same as 0 to 0. If the control qubit is 0, the target is being 1 as 1, right? If you take control qubit as 1, and now see the target qubit is acting like a NOT gate, right? Which is exactly X gate. It's gonna act like a 0 to 1, and when you take control qubit as 1, it's gonna go to the target qubit is changing from 1 to 0, right? You can observe that. So this control qubit and target qubit on the circuit, we should differentiate it. Like, are you applying are you saying that control qubit is this or this? That's why we're representing control qubit as a fill dot, which is this, and the target qubit, which is generalized as a B, as circle cross. Now, if you take control 0 and qubit 0 and qubit 0 and this as a fill dot and this as circle cross, or you can also represent it like this, but yeah, this is the basic representation of C naught gate in the normal circuit form. If you see this acts as a control one. So if it is 0, this is gonna change to 1. This is gonna remain as 0. If this qubit, which is control qubit, is 1, this is gonna change from 0 to 1, which simply acts as a NOT gate, as you can see here, the representation. So this is what a C0 gate is. Basically, you guys understood what a C0 gate does, right? If you this is a 2-qubit quantum logic gate where two qubits, one qubit acts as a control qubit, and one qubit acts as a target qubit. When control qubit is 1, the target qubit acts as a NOT gate. If the control qubit is 0, the target qubit is going to be the same. This is what a NOT gate is, right? Now, what is this matrix? Right, we've learned what a C NOT gate is. Now we're just representing that C NOT gate in the form of a matrix. Like we know that vectors can be represented in the form of matrices. What we learned till here is that this control, this is where did this come from? This is control qubit and this is target qubit, right? If we do a product, we get a state which is abcd transpose, which can be expressed in the form of two qubit system, right? We learned the two qubit operation, two qubit systems, where ket 00, ket 01, ket 10, ket 11 acts as a normal basis for the two qubit system. So this control qubit, oh, sorry for this. This control qubit and target qubit is gonna act like a going to do a tensor product, and we're gonna get this, which is basically the C naught matrix, where we see 1001, 010, 0001, 0001. This is basically the representation of this state, which, because if we're saying this exists in the two qubit Hilbert space or two qubit state, we have to represent it in the form of the basis. That's why we'll get a generalized matrix of C naught, that is 1000, 0100, 0001, and 0010. ABCD are nothing but probability amplitudes. Like A square is the probability of being this in this state. You guys know that, right? We've already learned it. So this symbol is basically known as Kronecker product. This combines both control and target, which gives us this superposition state. Superposition state, we express it in the form of uh, superposition of orthonormal basis states, which is ket 0, 0, ket 01, ket 10, and ket 11. And these are basically probability amplitudes, where we can say the probabilities from a square, b square, c square, and d square tells us about the probability of this existing probability of this state existing in this particular ket 00, and probability of this state existing in this particular ket 01 respectively. Okay. Now, as you can see, the operations ket 00 on a C naught gate operation is ket 00. Why? Let's consider this as a control qubit and the second one as a target qubit, right? If we consider this as a control qubit, see, the control qubit is obviously going to be the same, but the target qubit is not changing. That's what we discussed in the C naught gate, right? So when control is equal to 0, this bit is gonna not change. As you can see here, the same. The control qubit is 0. The 1 is remaining as 1. Now, let's see 10 and 11. The control qubit is being 1. So now the target qubit is changing from 0 to 1, which is a bit flip, right? The 0 bit is gonna change to 1. And here, as you can see in ket 11, this as the control bit is 1, this target qubit is undergoing a not gate, which is like bit flip and taking it to ket 10. So this tells us how that C naught works, and this is the action of C naught, right? Yeah. So basically that is C naught gate. I hope you guys understood what C naught gate is and why it is a 2 qubit uh, logic gate. And right, let's come to qubit gates. This is a special property, right? These have reversible logic. Okay, what is a reversible logic? What is this reversible logic? Why do we need this? Right, we have classical bits. We'll go to classical physics, where we have mini gates like and, or, not. Why do we need these gates? What is the importance of these gates? Right, let's take AND gate, right? As we can see the AND gate here. So what is reversible property does? The first thing is it's gonna preserve the information. Like when you take AND gate here, when you take A and B, the operation, the input you give, the output is going to be 0, and that's done. It's not going to preserve the information. It keeps losing the information as you give new inputs. The output is going to keep losing the information. Now here, what this reversible gate importance is that it will preserve the information. And the second thing is, if we have a reversible gate, the certain input will have unique output. Like if you take uh, a NOT gate, right? If you take 0 1, it'll be flipped to 0, right? So if we know the output, we can say what input is. That is basically the importance of reversible logic. The second important point is that you can say input based on the output. That we can't do in classical gates. So these are the two important points where we should like focus on. And the third thing is that these quantum gates which are reversible should always be unitary. As I told, the unitary is just that complex transpose of complex conjugate multiplied to itself should be equal to 1 I, which is identity matrix, right? So yeah, so this reversible logic is, the quantum gates gonna use this reversibility like this. So basically what I've explained. See, the quantum gates must be reversible, because otherwise it's gonna lose information which creates heat, right? And the second thing, classical gates like and destroy information, right? And see, and here all quantum gates are unitary, meaning they are reversible by applying the gate again. So these are the three important points, which one is going to preserve information, and two, the every single input has a unique output where input can be determined using the output. Third one is unitary. So these are the basic things what I just said. If you see, it must be reversible, no information is lost, and it's gonna preserve unlike the classical gates, it's gonna preserve the information. Like each input has a unique output, and it should be unitary. Every quantum gate should be unitary, and to exhibit or ensure that reversibility is present in that quantum gate. Some of the examples of these reversible gates are X, H, C naught. So these are all reversible and unitary. Okay, this is basically the reversible logic gates. Now, you guys understood what is the property of reversibility in quantum gates. Now let's see states generation. What is this? You guys learned about Shreyas explained you guys about entanglement, right? So we learned all kind of operations like single qubit operations, single qubit operations, two qubit operations. Now we'll ex- explore how we can use this qubits and get some meaningful outputs, right? We use these gates to get meaningful outputs. Okay, let's try getting one output using this operations we've learned till now, right? Okay, so first let's take ket 0 and ket 0, which is two single qubits, and we apply Hadamard gate, right? We know what Hadamard gate does. It's gonna convert one single qubit to two qubit system, which is basically this, right? You guys learned that in that Hadamard gate operation. And now, after this, you're gonna get this. Now I explained what is this. This is C naught, right? This is a C naught gate. This is the representation of the C naught gate. And this is the control qubit, symbol of control qubit, right? And this is the target qubit. This is how we know that this state depends on how the state will be, right? So now we have this output till now. Now what we're gonna do, we're gonna apply c naught gate to this output. We're gonna apply c naught, right? So first qubit is control and the next qubit is target, right? When control is 0, the target is not changing. See, and control is 1, the target qubit is acting as a bit flip, which is exactly the X gate, which is converting from 0 to 1, right? And you can see the difference, right? So now we'll get an output which is get 0 0 plus get 1 1 plus by root 2, which is just a normalization factor. But how you guys understood how we get this state from the state, right? Get 0 0, when the control bit is get 1, the target bit is going to do a bit flip, which we're going to result like this. So now we got an output. What is this output, right? What is this output? What are Bell states? We're going to see next state, but next slide, what are Bell states? But we got an output using two operations, which is Hadamard and one is C naught, right? So yeah, this is the Bell state. Now we're gonna see what are these Bell states, right? So Bell state, maximally entangled two qubit states. We have four types of Bell states, which is phi plus, phi minus, and psi plus and psi minus. So these four states are just like two qubit system bases. It's just normalization. When we take, you guys remember ket 0 0, ket 0 1, ket 1 0, ket 1 1, right? These Bell states are gonna act as orthonormal bases. Like, see, any two qubit state can be expressed as a linear combination of Bell states. It's just like, remember, single qubit state can be expressed as the linear combination of ket 0 and ket 1, right? So these Bell states should acts like a ket 0 and ket 1. Now you can see any two qubit state should be can be expressed as a linear combination of these Bell states. That's how we know that random two qubit state is existing in a two qubit Hilbert space. That's how we're gonna know, right? So these qubit states are nothing but two qubit states. One Bell state is phi plus, which is ket 0 0 plus ket 1 1 by root 2, and ket 0 and ket minus ket 1 1, which is just the phase difference by 180 degrees. And here psi plus is ket 0 1 plus ket 1 0 by root 2, and psi minus is ket 0 1 minus ket 1 0 by root 2. As we see that we just saw how this state is generated, right? Now we can generate all these three, like from the operations we are using, we can generate all these three states. We'll see all this how we generated all these states in the simulation. Now this is till the topic. Now I'll hand over it to Shreyas to continue the simulation hands-on activity. Thank you.
All right, guys. Now let's just move on to the simulation. Let me just share my screen. All right. I hope this is visible. This is just a website called algesser.com/work. It's a online free to use website where one can simulate simple quantum circuits. There are several provisions here. You can see a diagram similar to the one Lippi used while explaining entanglement, where these represent the qubit streams. You can place any gate you want here in order to manipulate your circuit. You can use controls in order to merge different qubits. Here you can see this is just the measure probability measurement. um Say at the moment it's just get zero, right? So the probability of being on if measured is 0%, same as the case here. This is the block sphere representation. You can see the values, the spherical coordinate values, and this is not this is nothing but the final amplitudes. This state is 0 0 0 1 1 0 and 1 1 states. Normally when we have just a singular qubit, say get 0 or get 0, then only the 0 0 part is enabled, and you can see the amplitude here as well. So first, here you can see that this thing, first let's look at the simplest of them all, which is the X gate. Now here this is the X gate, but you can see that it's also represented as the target bit. Both effectively perform the same function, so they have provided the small mechanism that indicates both are the same. I put this here. So you can see that the qubit 0, it's passed through the X gate, and now the chance of being measured, being on if measured, is 100%. You can see the block state representation here as well. You can see that it now points downwards towards the south pole, which is basically a representation of ket 1. Here you can see 0 1 as well, because we have it at ket 1, so it'll be amplitude of 0 1 alone is enabled. um this is with respect to just ket 0 as well as ket 1 representations. Um now let's take a look at X. We took a look at X on ket 0. Let's take a look at X operating on ket 1, which just I just want to add another poly X here. So you can see that ket 1, this thing represents ket 1. In order to show you that, I have another nice function here called a probability display. You can see that it basically shows the chances of an outcome if a measurement were performed. It uses controls to see the conditional probabilities. Now, look at the wording here. Very interesting wording. It says it shows the chances of outcomes if a measurement were performed. Now, you might ask, what's the difference between shows the chances when measured and shows the chances of an outcome if a measurement were performed? They are completely different statements, because in the quantum realm, you have to remember that the act of performing a measurement itself alters your final values. So it's always better to have something like a probability display, so you know where you're standing with respect to your circuit creation before you move on. For example, I have 0 here. I put a pass it through an X gate, should be ket 1 here, but let me just verify that. See, you can say that it says on, which means it's on ket 1. Now if I put a X here, doesn't matter. This is not affected, because this just shows you the chance of shows you the result of whatever is there before it, and that too if a measurement were done. See, you can also see here also a chance of being on if measured, and that's something. You can also see the amplitude. You can also see the amplitudes. You can just put it here like that. um Amplitudes are generally, if you want to see the amplitude of your state itself currently, like so. Um now before now that we looked at the X gate on 0, X gate on 1, as you can be see. Now let's take a look at the Y gate. The Y, let me just create a 1 here. So this is just the 1 by default. This is the 0. And now the 0 on the Y gate, you can see this and the block sphere representation and this remain the same. But it is in the amplitudes where the actual fun stuff is there. You can see that the amplitude of 0 0 or 0 1 both remain blank, as compared to when I put X. Just a second. You can see that normally it's 0 0. When I put an X, it goes to 0 1. when I put a y operator, when I put a y operator, you can see that the amplitude has shifted by 90 degrees, which is what we expected to happen. Now let's also see the effect of the y gate on ket 1, effect of y gate on ket 1, which is basically, before we this is ket 1, the effect of y gate on ket 1, you can see that as well. And then let's look at the effect of the poly z on. Now let's look at the effect of poly z, which is just get 0, put z, and artificially create before that like 0, I put a z. You can see that you can see the amplitude here, and I show the effect on this as well. You can see that it just with respect to 1, the phase, it's just that the phase of 1 alone goes a flip. This is the 1, and the phase of 1 alone, you can see it just flips, if you are able to spot it. This is just get 1 at the moment, and now I put a z gate, and you can see 0 remains the same, whereas 1 alone just flips, which is what we expected would happen. um some other simple gates include your s gate, our s gate. You can see the effect of s gate on ket 0, and you can see the effect of the s gate on ket 1, and you can also see the effect of the t gate on ket 0. T gate on ket 0 is just remains rather unchanged. Now t gate on ket 1 is where the special effects are. Mm, you can see that the phase of e to the power I pi by 4, or the is added, or the phase has undergone a change of plus 45 degrees, if you're able to observe. And that's the t gate operating on kit 1. You can also use chance here. See that it is on because I operated an x gate on kit 0. Let's look at Hadamard as well. The h gate on kit 0 results in an equal superposition. You can see 50%. You can see, if you may remember, the h on ket 0 will result in ket plus. The ket plus is an equal superposition. You can see 50% chance of being on the block sphere representation as well. And a magnitude, you can see that the amplitude of 0 0 and amplitude of 0 1 both remain the same. Now let's take a look at the effect of the H Hadamard on kit 1 as well. Hadamard, I'm sorry, just a second. Yeah, yeah. You can also see the effect of Hadamard on kit, still in equal superposition because both are 50%. However, you can see that the amplitudes vary. The amplitude of ket 1 is the opposite of ket 0, which is again what we expected, because H on ket 0 will result in a ket minus t. Now, Lipi will take over and explain the 2-qubit systems in the simulation.
Thank you, Shreyas. Yeah, you guys can see, right? Till now, he explained how single qubit operations can be operated by seeing this explanation. Now I'm gonna see how I'm gonna explain you guys how 2-qubit operations are. Right? We've seen. Okay, first we'll see C naught gate, which is X and C naught. Target qubit is same as she has explained. This is a C naught gate, right? It's both are and off because this doesn't mean anything. You just have to apply. It is in single qubit system, but what does this does? It applies to a 2-qubit system, right? So both are in off condition as we have no gate before to C naught to work on. There should be Hadamard gate to convert that single qubit systems into 2-qubit system for C naught gate to work, right? So now what we'll do is that for you guys to understand what how two qubit operations, right, is that we've seen Bell states, right? We'll try to generate that Bell states in the stimulation, right? Um, we'll see the first Bell state where we took first Hadamard gate, right? We'll apply this Hadamard gate to qubit 0, which is first qubit. For our convenience, we'll say it as Q1, which is qubit 1, right? We'll apply in Hadamard gate. Now you can see, which is C ket 00 plus ket 10 by root 2. You got the Hadamard gate, right? This is the Hadamard gate representation. See, the values is plus 0.7, which we actually expect 1 by root 2, right? The phases are 0, as there is no minus in this, it's only plus, right? Now we'll till that we got this is the we got the output of what we should get in by using Hadamard gate. Now we'll see C naught. We're gonna give the priority to qubit 1 and take initiative as control qubit, and this is the target qubit, right? See, now you guys can see this is ket 00, right? This is ket 00, and this is ket 11, which we know the Bell state where 5 plus is ket 00 plus ket 11 by root 2. As you can see, the amplitude, see, plus 0.7, which is 1 by root 2, and here plus 0.7, which is 1 by root 2. But here the phases are 0, as there is no phase difference, the sign remains same, right? And the magnitudes, the probabilities are 50% and 50, as the alpha and beta, if we take it in generalized form, 1 by root 2, the probability is 1 by 2, which is 50% and 50%, right? So this is the first Bell state, right? And as you can see here, the probability, the chance of being on is 50%, and chance of being on is 50%. um, Here this is a block sphere representation, right? We'll see the theta angle as plus 90 and plus 90, right? Now we'll go to second Bell state. We'll generate second Bell state. Same as the before one, we'll take two qubits, which is Q1 and Q2, and we'll apply Hadamard gate as usual, because we have to apply Hadamard gate to convert the single qubit to two qubit system, as we have to apply C naught gate to get the Bell states, right? So we are applying Hadamard gate, we'll get the output as ket 00 plus ket 10. You understood what this square is meaning, right? This is ket 00, ket 10, ket 01, and ket 11. This is what it actually means. You understood that, right? So whenever the circle appears in this boxes, it represents that is being on that position. So when you apply Hadamard gate, it shows ket 00 plus ket 10 by root 2. And that is why it gives 50%, which is 1 by root 2, right? The probability is 50%. Now we're gonna apply C naught gate. We're gonna give the control to qubit 1 and target to qubit 2. Okay. Now after applying C naught, you guys can see ket 00 and ket 11. Now we've got the first qubit, which is 5 plus, right? Now what is the difference between 5 plus and 5 minus? Phase angle. We have to change the phase angle. And what is the operation for that operator we use to change the phase? You guys know that, right? That is Z. Now we're gonna take, see, the phase is gonna change. That's why we are using Z to change the phase. We're gonna apply the Z to qubit 1. See, now you guys can see the phase difference, right? So this is the difference between 5 plus and 5 minus. The phase is gonna change. This is the value amplitude is gonna be 0.7, which is 1 by root 2, and here it's gonna be minus 0.7, which is the phase. See, the amplitude is going to be minus, guys, because we're applying z, and we're going to get 0, 0 minus get 1, 1 by root 2, which is exactly the sign minus. And here the phase angle is 180 degrees. That's why we get minus. So this is the second Bell state, right? And now we'll go for third Bell state. Yeah. So as usual, we're gonna apply Hermite gate to convert the single qubit system to two qubit system. Now we're gonna use the C0 gate, and we're gonna assign Q1. As you can see, I'm applying this to Q1. You can do this too. You can assign this control qubit to get Q2. But for my convenience, I'm taking Q1, and we're gonna apply target gate here. Now we'll get phi plus, which is the first Bell state. Now what we're gonna do? What is the difference we have to get? We have to get zero ket 01 plus ket 10 by root 2. How are we gonna get that? We're gonna use X gate to change to do a bit flip, which is a toggle is same as the bit flip, right? See, now you guys can see this is ket 01 plus ket 10 by root 2, right? The phase is gonna be the same. This is exactly what is the third Bell state, which is psi plus. As you guys can see, now I'm taking this as like this state, this gate, particular gate. You guys can generate it using any type of gate in a different way. I'm using this manner as I'm convenient with this, but you guys can play with it. Now, see, now you'll get the third Bell state, which is ket 01 plus ket 10 by root 2. Now, we'll go to fourth gate generation, uh, which is fourth entangled state is psi minus, which is get 01 minus get 10 by root 2. Now, how are we going to generate that? From single qubit, which is get 0 and get 0. Right, first we're going to apply Hermite gate to convert get 0 to two qubit system, single qubit system to two qubit system as ket 0 0 ket 1 plus ket 10 by root 2. Till now we knew that, and now we're gonna use this C0 gate, and you guys will get the first Bell state, which is phi plus, right? Now what are we gonna do is that we need both phase difference and what do you call bit flip. So what gates are we gonna use? We're gonna use two gates, which causes bit flip and which causes phase difference. One is, you guys know that Z generates the bit flip. Z generates, like, it changes the phase of the given thing, and X is gonna do the job what NOT gate does. See, when you remove this, when you remove X, it's gonna be in 0 0 and 1 1. If you put X, you're gonna get 0 1 and 1 0. This is how it works, right? So this is exactly 0 ket 0 1 minus ket 10 by root 2. See, if you remove Z, this phase is not changing. If you put Z, the phase is gonna change. That's exactly what Z gate does. And what X gate does is that not bit flip, right? You guys understood that. So this is the last bit state, which is get 10 and get 0 1 minus get 10 by root. And now you guys understood how we can generate different types of states. I've gave a brief of how to generate two qubit systems on this simulator. You can generate any type of qubits using this, right? So yeah, you guys can see this website, which is Quirk, and if you make a like circuit kind of thing. You can save it by bookmark and export it, like send it to other people, like this, right? So that's it on my side. I hope you guys understood how the stimulator works.
Thank you so much for joining us,
Thank you so
and
much.
we hope you had a good time.
We hope you guys understood what quantum computing is.
Yeah. No, it would be surprising if you guys understood everything, but I just hope you guys know how much of it you don't understand. That's basically our goal.
Yeah. Guys, the attendance link has been shared. Please fill the attendance link, and you're free to leave. Thank you, guys.